Okay, our next topic is design consideration of micro devices or microsystems. And uh, the previous lecture was on the selection of the materials. I mean, the consideration of the materials for MEMS or micro devices. Then next, we will discuss on the how we can look into the design itself and what should be considered. So and the consideration is with regard of the materials, with regard of the requirement of the application, etc. I mean, will be discussed. So in general consideration, and designing micro electromechanical systems or MEMS requires a holistic approach as the behavior of the devices at the micro scale is governed by different physical principles than the macro scale systems. Design decisions are highly interconnected, affecting performance, manufacturability, and reliability. As discussed previously, we know that in the micro scale or nanoscale, the Newtonian mechanics not functioning as what we understand at the macro scale. So at the micro scale, sometimes the behavior, I mean, if we do not consider accordingly at the micro scale or nanoscale, we won't get the intended performance of the device because some of the material, some of the properties of the material change at the micro scale, and we don't get the exact property as the macro scale, then the intended device performance won't be obtained. So then we have to look firstly on the material selection. So the choice of materials fundamentally dictates a device performance, fabrication process, and reliability. So just now we have a look into the silicon itself. So silicon is the most common MEMS materials due to its well-established fabrication process inherited from the semiconductor industry. It is lightweight, has excellent mechanical properties, elastic, no creep below 800 degrees Celsius, and allow for integration of electronics on the same substrate. So I think I've been talking about making a circuit design on top of the silicon substrate. So this is the meaning here. The integration of the electronics or the electrical circuitry on the substrate itself is important. So we know that in other device, in the macro scale device, we can have the electric circuitry deep, I mean, with a wired uh, winding on the device or with a electronic circuit at different outside of the device, etc. But for micro scale device, we need to layer the electrical circuit on the surface because we want to maintain the small structure and want to make it accessible for the small places that we want the intended application. So single silicon crystal, highly stable but anisotropic with properties that vary based on crystal orientation. And polysilicon, a versatile material used for structural layers in surface micromachining. Its properties depend on deposition condition. So, and for metals, used for electrical interconnects, I think we have discussed this, high aspect ratio structure. High aspect ratio meaning you have, let's say, long-standing materials. So, meaning the width and the length are pretty much different in terms of the size. So that is the meaning of high aspect ratio. And properties like residual stress and adhesion are critical consideration for metal thin films. So, for example, we have a gold, high electrical conductivity and corrosion resistant, but requires an adhesion promoter. We have discussed it. If we use chromium, for example, we can get good high adhesion with the surface. And nickel, ferromagnetic and good mechanical properties for a structural application, often used in a Liga process. and polymers used for flexible structures and in biomems due to biocompatibility, flexibility, and cost effectiveness. Example of a polymer is SU8 and PDMS. These are quite common material in MEMS and biomems application as well. So you want to make a structural, you can make a structural design using this kind of material because of its high viscosity. And ceramics used for their strength, high temperature stability, and piezoelectric properties. Piezoelectric properties for ceramic, for example, the PZT, PBZrTiO3, for example. An example includes silicon nitride and aluminum nitride. Then another consideration, we have gone through this in previous class, the scaling laws. Again, when we design something at the micro scale, the scaling, I mean, I keep mentioning this a few times, the scaling law. At the micro scale, physical phenomena scale differently with size, meaning that design cannot be simply scaled down from the macro world. So if you think that at the macro world, you design something, then you just shrink it, shrink the size, everything, it will work accordingly as what you have at the macro world, then you are wrong, basically. So you have to maybe alter the design and consider different materials in order to make it work, because the property will change significantly when you scale down to the different size. Surface to volume ratio, as device shrink, surface area dependent forces such as friction, adhesion, surface tension become dominant over volume dependent forces like inertia, mass, and weight. This is critical for actuators, microfluidics, and heat transfer. So we had a look yesterday on the how you can your properties of the material effect when you scale down the size. So some property change 1,000 times. For example, force change 1,000 times when you make 10 times smaller in terms of the size of the device. So that is significantly reduce the forces required, I mean, can be exerted by the device itself. Then you need to think of how you can get, I mean, sufficient enough forces if you design something. Means something small. So dominant forces in fluid dynamics at the micro scale, viscous forces dominate over initial forces due to low Reynolds number. This requires different strategies for fluid movement than those in a macro scale system. We need to say if you have too small channel for liquid to flow, the capillary effect will work, right? I mean, if you stand that, you can see that the liquid will go up if it's a very small, narrow channel. But that is a place where you can play with capillary, for example, if it's small. But of course, at a certain extent, you need to look into the viscosity of the fluid, etc. So by design, you have to consider all those things in terms of what are the dominant forces. And the thermal properties, you need to consider heat dissipation, which is surface area dependent, becomes more efficient in smaller scale relative to heat storage, while is volume dependent. This can influence the design in thermally actuated devices. So for example, when I showed you yesterday on the use of inject of the liquid, so with a thermally actuated actuator, if it's very small, you can heat up the materials quite fast. So the time to deform the material at a faster rate will make it possible for you to use a high frequency, let's say, inkjet printer. So that is part of the thing. But the thing is, at the small scale, you can heat up something quite fast, but the heat also will disperse quite fast as well. So that is the things that will be things need to be considered in the design of the related to thermal properties of the material. And stress and stiction. So these are major reliability challenges in MEMS that must be addressed during the design. So the stress to the structure is different. So, and stiction meaning it tend to attach with the surface. So it stick, you know that if something very small is easily stick to surface of a material, so stiction it prevent things from moving. So that is part of the thing that you need to consider when you design a very small device or structure. And residual stress, internal stress remaining in a film after fabrication can cause warping, cracking, or buckling, altering device performance and reliability. So, as I mentioned in the previous lecture, this residual stress is according to the fabrication process parameters as well. So, if you want to reduce the residual stress or try to mitigate the residual stress, so partly we can look into the design technique, include using corrugated beams or incorporating features that relieve stress, and process optimization, such as controlling deposition parameters, is also used. So this is what I've mentioned before. I mean, we try to, but this need to be a kind of a recipe that already established, or if it's a new process, we need to identify or to try to optimize the process itself in order to get low residual stress materials or acceptable residual stress of the material. And stiction, the unwanted addition of released microstructures to the substrate or other parts due to surface forces. It is a primary cause of device failure. So when the stiction happens, you get your maybe actuator won't be able to release something from the surface, for example, because it's a stick or a kind of glued to the surface, basically, is the stiction. So that is the things that we have to prevent. So the mitigation, surface modification, so applying anti-stiction coatings, for example, like hydrophobic monolayers can reduce surface energy and adhesive forces. And surface texturing, increasing the surface roughness, reduce the contact area between components and thereby reducing stiction. And mechanical design, incorporating spring-like structures or bump stops can prevent stiction upon contact. Let's say you have some actuator that force something to go to certain surface, but at a certain extent, if it's touch the things, you have a spring property of the material to come back to its original position. That is one of the maybe strategy in terms of mechanical design. And same goes with texturing. We know that if the surface is too flat or too smooth, then it can also be a stiction surface. Then you try to make it more rough. And another key consideration is fabrication and manufacturability. So how easy you can fabricate, how difficult it will be if you choose certain design or certain materials. So MEMS design is highly dependent on manufacturing capabilities and process variation. So in MEMS design, basically you have a number of process that already established within the use of semiconductor. So you try to use this process as far as you can in order to prevent unnecessarily hassle. In process of machining process, for example, you use forces in removing of materials. Let's say you do drilling, you do cutting using lathe, for example. And then, but for MEMS process at the small scale, we can say that the MEMS devices are fragile in comparison with the macro scale devices. So you want to avoid the application of forces to the materials as much as you can. So you want to stick with the process that already established within the semiconductor process in order to make sure that you can fabricate the materials or the device successfully. So fabrication process, I mean, once we design the device or the micro devices, we have to have in mind on the process flow, what to do and how to create what kind of structure. So that will make sure that the device will go through the process which the semiconductor process which is already established without going into let's say mechanical process of drilling, etc. So fabrication process, the choice between bulk micromachining, etching into the substrate, for example, and surface micromachining, depositing and patterning layers determines the device geometry and complexity. So because of it's a small scale, it's always complex devices. You cannot simply handle it with hand of the microstructure, everything, but you need to handle with care, and you need to look. I mean, in terms of process, sometimes or most of the time, we need to see under the microscope because of its small structure. So the naked eye will be difficult. So that's where you need to design accordingly with the even the structural design is difficult for you to fabricate basically because the original of the MEM process is basically semiconductor process, which is surface micromachining surface process. So or 2D. So design for manufacturing, this is part of the consideration, a strategy that links design and fabrication to improve yield and reliability. Is involved using systematic design principle and a robust model to account for process variation. So sometimes certain process does not work. For example, you need to think of certain process and sometimes you need to maybe redesign of your process steps in order for you to obtain certain structure. So process imperfection, manufacturing tolerance such as variation in beam thickness or photolithography alignment can impact device performance. Designers must model these imperfections to predict their effects. By design, we might consider, let's say, want to produce a 50 micrometer thickness of beam. So, but in the process, we have to go through certain process of masking, etc. So the the parameters in the process will not accurately, sometimes it's not as accurate as what we want, then it have a variation in terms of the process parameter, then we cannot obtain the size as intended. The 50 micrometer might be maybe 40 less than what we want, or it might be bigger, maybe 60 micrometer in terms of thickness of the beam. So we have to consider of this kind of variation when we design something. But sometimes the process is well established. We know that if we want to obtain the size of 50 micrometer, we have to design the process flow, the masking, etc., with a slightly bigger. For example, if you want to obtain the final beam size of 50 micrometer, you have to make your design in terms of your mask, photo mask, like 55 micrometer, slightly bigger. So that might be the things that maybe experienced MEM fabricator can do. And process, same thing. So packaging, unlike macro device, MEMS often require special packaging to function and function properly while protecting sensitive components from the environment. So as I mentioned before, MEMS need to be packaged because of its small nature. You want to prevent it from a shock, you want to prevent it from environment, for example. I mean, to protect from even dust, then you need to have a proper packaging. Functional requirement, the packaging must allow for sensing or actuating functionality of the MEMS device, which often means exposing it to the external environment. This creates a conflict with the goal of protecting the internal electronics. So this kind of trade-off you have to consider. You want it to function, let's say your MEMS speaker, for example, some parts need to be exposed so that it will behave like a speaker. You can hear the voice, but at a certain extent, the some of the small part you need to protect with the packaging. So that kind of thing need to be considered. And environmental protection, packaging must protect against moisture, chemicals, mechanical shock, and other environmental factors while allowing for the necessary sensing part. So that is what needs to be done as well. And another design consideration is the material properties. We have been talking about this as well. Coefficient of thermal expansion. A mismatch between the MEMS die and package material can induce significant mechanical stress and affect performance. Material selection for packaging must minimize this mismatch. So you have different materials. Let's say your packaging is something like polymer. So polymer does not, expand that much. And some parts of your MEMS device might use certain metals as the structure, for example. So the expansion of the metals is higher with temperature. So this mismatch of expansion, thermal expansion, will create stress to the packaging and to the design, the microstructure of the device itself. So this kind of microstructural material mismatch in terms of thermal properties need to be considered on how you can release or to make sure it won't break when it happens. So, or in a controlled environment of the operation. And option package types, option range from standard, cost-effective, full mold package for consumer products to more stable, higher performance cavity or hermetic package. So this is a type of package that you can consider. Then another key consideration for the design is on the actuator itself. The transduction and electric interface, the physical phenomenon being measured must be effectively converted into electrical signal and routed to the control electronics. So basically in MEMS device, you need to have things to move, and maybe it depends on what application. If it's about sensor, you need to have a sensing part that can sense or change the property or respond to the what you want to sense, even if it's heat, it's light, or it's humidity, whatever things that you want to it react to. Then you have to consider the phenomena accordingly and what will be the electronics of the things that you want to sense. So this kind of consideration, for example, transduction method, this is a core design choice with a common methods including capacitive, piezoresistive, piezoelectric, and thermal. So transducer basically, or actuator that can be used and normally used in MEMS is as this capacitive sensor or capacitive transducer. It can be sensor or it can be transducer. Normally both way, but it depends on the application. So whether you want to use the capacitive as a sensor or capacitive as a transducer. So in application, if you want to move something, it becomes a transducer. But if you want to sense a movement with capacitive, you can how much is moved. So it depends on your application. It goes the same with a piezoresistive, piezoelectric, and thermal. We know that piezoelectric will have a sensing property. When you provide electrical current to the piezoelectric material, you can have expansion. So the material will expand and it become actuator. But if you apply strain to the material, you can get electricity to, some sensing because it induces electricity. Okay, so it's same with goes with thermal. So electrostatic actuation. So the forces generated depend on the spacing and configuration of electrodes. So in devices like vibrating gyroscope, the placement of driving, sensing, and tuning electrode is critical for performance. Electrostatic, I think we had a look yesterday on the electrostatic actuation, and some example of the COM drive actuator, right? COM drive is basically electrostatic actuator. So with COM drive, you can have a different configuration in terms of getting the electrostatic forces. If you make it, become more COM drive in kind of integrated electrode, you can have higher forces basically. And signal integrity, the electrical interface must be designed to minimize noise and interference, especially for highly sensitive analog and digital MEMS signal. So this is an example of a design consideration. So we have a look at the overall, the general design consideration for micro devices. This is, the next is on the example. So let's say you want to have this kind of pressure sensor. You have a layer of thin film here. This is a bulk substrate, kind of anchor. So you have the change of pressure from here, from the bottom. So when the pressure change, this device, this thin layer is the place that you want to sense the what has been changed. So with the change, the deformation of this thin film, you want to have a signal. So basically, you can use piezoresistive or thermal or anything that related, because with the change of this, let's say you use piezoelectric, for example, the deformation of this layer will provide some electric current to flow. Then you can say, depend on the calibration, you can sense the pressure of the, what happened inside if the pressure change. And another design here with a cantilever. So this is, in MEMS device, is always revolve about the change of deformation of something. So let's say here is about deformation of this thin film, this maybe the deformation of this cantilever, the movement of this cantilever, and with certain gap here. So if it's touch this surface, then you might get electric to flow, for example. So this electrode, pull down electrode is electrostatic or capacitive. So you can pull down this to provide a signal, electric to flow. So this is an anchor. So you must make sure that your design is robust enough and the gap is sufficient, for example. So this will be the design consideration that you have to consider from the beginning. And for you to, this is part of the material consideration. But on top of that, you have to consider, as I mentioned before, the process itself, the process flow. How can you fabricate this over, let's say you start with silicon, then deposition of this layer and this layer, etc., and how you can make into this geometry, etc., should be considered from the beginning of your design. And we look into elasticity of the material. So the ability of a body to deform in response to applied forces and to recover its original shape when the forces are removed. So we want, if we talk about, let's say, the diaphragm here, so you will have this in terms of pressure change, there's this deform, So how elastic is it to come back to its original position, and whether it will go through fatigue, etc., and maybe plastic deformation. So that is thing that you should consider as well. And contrast with the plasticity, which describe permanent deformation under load. So if over the elastic deformation, so some material will experience plasticity. So when you go to the plastic region, then the shape won't come back to its original shape. So elasticity is described in terms of differential volume elements to which distributed forces are applied. So we have to look into the strain. Strain is a continuum description of deformation, and center of mass translation and rigid rotation are not strain. And strain is expressed in terms of the displacement of each point in a differential volume, where micron or u is the displacement and x is the original coordinate. Okay, deformation is present only when certain derivative of this displacement is a u or non-zero. So with different regimes, so how are stress and strain related? It depends on the regime in which you are operating. So if the regime, the range is still within linear or non-linear, linear strain is proportional to stress, and most things start out linear. And for elastic versus plastic, and deformation is recovered when the load is removed. This is elastic, and plastic is some deformation remain when unloaded. So if plastic deformation happen, then you won't get, the device at what as intended. Isotropic versus anisotropic. Life is simpler when properties are the same in all directions. However, anisotropic silicon is part of life, because silicon crystal, single crystal silicon is with orientation fixed. Then different side of the silicon will give you different property. So if you want to etch the silicon into shape, then you have to consider the orientation of the crystal. So that's where identification of the crystal orientation from the beginning will be crucial. Okay, thin film stress. Thin film on a substrate can have residual stress, whether intrinsic stress or thermal stress. So if you want to deposit thin film, let's say you have substrate deposit thin film with certain stress, so a certain process. So the addition of this thin film on this substrate will have a certain stress, which we call as intrinsic stress. It's due to the process, as I mentioned before. So mostly described as a plane stress. So especially if you see at the edge, if a stress happen, so you will get the warpage at the edge of the thin film. So that is the what happened if intrinsic stress. So what we have just talked about is elastic strain. Strain caused by loading returns to undeformed configuration when load is removed, and described by the isotropic equation of linear elasticity. And there are other kinds of strain as well. Thermal strain, which is related to thermal expansion. So when thermal expansion happens, so some materials will have a thermal strain where it doesn't go back to this original position or original shape. Thermal strain, which is related to thermal expansion. Plastic strain, if you stretch something too far, it doesn't return to its undeformed configuration when the load is removed. And total strain is sum of all these strain. So some device experience the total strain. You have a lot of strain. The intrinsic strain, the thermal strain, etc. Then it will affect the performance of the device as well. And thermally induced residual stress. If a thin film is adhered to a substrate, a mismatch of thermal expansion coefficient between film and substrate can lead to stress in the film. So this we have discussed before as well. you have a different material. Of course, you have a different thermal coefficient expansion. So if the device experience thermal or heat, then the expansion is different between your substrate and your deposited thin film, then thermal strain will happen. So the mismatch in terms of the coefficient of thermal expansion will cause this. So the stress also set up bending moments. You can care about this if you don't want your wafer to curl up like a saucer or potato chips. Sometimes you have, because you make it into thin film, so your device, due to the addition, strong addition, but the strain of your deposited film might cause the warpage or the bending of your surface of the material. So that is what quite commonly happen if you don't really take care of this in the beginning. And the vertical expansion of the film is also modified. So intrinsic residual stress, any thin film residual stress that cannot be explained by thermal expansion mismatch is called the intrinsic stress. So source of intrinsic stress, deposition far from equilibrium. So meaning when you deposit the thin film, it's not in the equilibrium state. So secondary grain growth can modify stress as well. So you growth the material layer by layer, but the secondary growth, for example, the next growth is modify the stress of the thin film. Ion implantation can produce compressive stress as well, and substitutional impurities can modify stress. So it's not that easy to control the purity. So sometimes we have a different element to be included in the material. Even with a small amount, it can change the property of the materials. Then we talk about plastic deformation as well. Plastic deformation, if the material happen to experience deformation over the elastic deformation, it will go to plastic region, then it will come back to the original shape. So beyond the yield point, a plastic material develops a permanent set, and this is exploited in the bending and stamping of metals, basically. It can be something useful, but in the device itself, it depends on the device intended performance and capability. And brittle and ductile materials, for example, if something brittle, silicon is basically brittle. So it's hard and brittle. So you don't want to drop the silicon because it will become like a glass, for example. Then, of course, if you want to use something in more careful, then if it's brittle, then you have to consider the brittleness of the materials and the intended application of the material. And of course, you have to look into material with, if it's ductile, what will be the region for plastic deformation. And I would like to share an example of the design consideration of a device, which is called microenergy scavenging. So in this device design, we have to consider a few things in the design in the early stage, and for the process itself and for the intended application. For the intended application. And what I'm going to share is a device which is called microenergy scavenging, a microenergy conversion device, a miniature system that convert available energy into a more useful form, such as the conversion of chemical, thermal, or solar energy into electrical power, propulsion, or cooling. We can have a lot of this kind of device at the small scale. People try to design this kind of energy scavenging device using piezoelectrics, where you have a strain or you can have a vibration, then you convert into electricity. So it can be as small as nanowatt or nanoampere, but the thing is with different energy source. So in piezoelectric, for example, it can be the strain or vibration or deformation happen by any means that can deform or provide strain to the materials. And another thing is on the uh, thermal, for example. For thermal, you can have energy scavenging, micro energy scavenging materials such as thermoelectric or pyroelectric, so that when you have heat source, you can convert uh, in a solid using a solid state material to convert the heat into electricity. So for thermoelectric, you can convert due to uh, heat or temperature difference, and for pyroelectric, you convert due to temperature fluctuation. And of course, you have a solar energy using solar cell, etc. So, but we are talking the things at the small scale, so micro energy scavenging. So for this kind of device, I mean, you can have a different source from human motion, wind energy, and raindrop, thermal energy, and solar energy as well. Now you want to have a small device that can maybe at certain extent used to power up a sensor node, a small devices with maybe milliwatt, microwatt, or nanowatt sensor. Okay, and the source can be from environment excitation, mechanical vibration, as I mentioned, even from you convert into electrical energy, or the other way around. Then electrical energy output will be what is actually what you want in terms of energy scavenging. And of course, in the conversion, you need to consider the amount of energy that can be harvested, okay, and how much you can convert into useful energy or electricity. So here, the objective of this device to develop a process for fabrication of microarrays directly on flexible electrospun beta phase polyvinyl fluoride PVDF film. So why is it the objective is important? Because you want to determine your device size, device structure, device materials, etc. So here you see that is uh, with a microarray. So why is it microarray? Because this is about a small device. So you use PVDF as the conversion of PVDF into useful energy is very minimum, very small. Then with a microarray, then you can combine like arrangement of battery in terms of series, so that you can get higher power output. So and flexible electrospun beta phase basically is the best phase of the PVDF in terms of uh, producing electricity. So the materials used is PVDF, polyvinyl fluoride. So the fact of a PVDF is a copolymers, most extensively studied polymers for piezoelectric generators, and high resistivity towards Morse chemical. Basically, is quite inert and oxidant and intense ultraviolet light. And PVDF have uh, 5 different polymorphs, which is alpha, beta, gamma, and delta, and epsilon. So you have different phase of PVDF, alpha phase, beta phase here, and sigma phase, gamma phase, I mean, gamma phase. Then with different phase, basically you have different properties. So the property of the phases is important here, because you want to use it as energy scavenging or try to convert the heat into electricity. So you want to have the best property for heat and for the strain, because it's about a pyroelectric property. So the most influential and typical phases, alpha phase, the axis of the chain and the dipole components are anti-parallel, thus neutralizing each other. And the naturally occurred alpha phase is categorized as non-polar and non-piezoelectric. So we want to have a piezoelectric property, so we cannot use alpha phase basically. And the beta phase, the dipole components are parallel, hence result in greater spontaneous polarization. And this type of conformation displaying pronounced ferroelectric and piezoelectric properties. So basically, beta, that is the reason that we choose to have a beta phase PVDF in terms of the selection of the material for this energy scavenging device. So, okay, this is the PVDF film synthesis. The synthesis of beta phase content PVDF using electrospinning. So I'm not sure if you are familiar with electrospinning. Electrospinning is a process where you apply a high potential between two terminals. So you put your liquid PVDF in a shearing, then you control the shearing forces, applied pressure, then you control your potential between these two terminals at high voltage, basically, high potential. Then you can have a strain of nano strain to be, pulled from the shearing. So that is the process of electrospinning. So with this process, basically, we'll be able to produce high beta phase PVDF. And as you are aware that piezoelectric needs to be pulled, the polling process needs to be done. But in this process of electrospinning, the polling can be omitted because the process itself with a high potential is already a process of polling. So beta phase fraction of the electrospun VDF film will be determined using FTIR, etc., to confirm the properties, and then with a micro patterning and integration of PVDF microarrays and electrical performance of energy harvester. So this is the PVDF string or thread. This is the film basically. If you zoom this film, you can see this kind of thread. Then you can make it into microarrays as intended. So all connected with circuit with a metal circuit. This has been produced using reactive ion etching to make into micro scale device. Okay, okay. This is the process of electrospinning. So as I explained before, you have a shearing, you have a drum here. So you apply 10 to 15 kilovolt in between this, then you can get the PVDF on this rotating drum. So you can get this kind of thin film and with this kind of strength. Okay, this is the process of micro patterning and integration of this PVDF microarrays. Basically, we use flexible substrate instead of silicon. So the flexible substrate can be a kind of polymer or something. It can be plastic, a suitable material with a certain adhesive, polymer adhesive. You attach the electrospun PVDF on top of this substrate. Then we use stencil mask basically to make a pattern. So the pattern intended is like this kind of pattern basically. That's what we want to make. Okay. So setting stencil mask, then you make a pattern here with stencil pattern stencil mask. Then you do the micro patterning of this electrospun PVDF. So you get the shape of the patterning. So in order for you to get this shape, of course, you have to remove this material, this electrospun film, using chemical etching. So the process in details, it involve, this is quite normal in terms of micro device design, to go through this kind of process, pre-baking of flexible substrate at this 65 degrees Celsius for 2 minutes, then spin coat photoresist, as I mentioned before. We will look into photoresist properties later on. Then hand rolling electrospun PVDF on the substrate, curing for 80 degrees Celsius, and micro-patterning using reactive ion etching. So this is the substrate. Then you get this kind of mask. Basically, this is the mask, stencil mask. Then this is the electrospun PVDF at the bottom of this mask. So this is where you try to transfer the pattern of this stencil mask to the substrate. Then you do the reactive ion etching. Then this is the result. I mean, the clamping here to hold the stencil mask, the spacer. You need some spacer. Then electrospun PVDF, adhesive. Then patterning of the deep RIE with a gas flow rate of oxygen and pressure, RF power, etc. You do the etching of this PVDF membrane. Then this is quite important parameters for a certain process, because, I mean, depend on the material that you are dealing with, the process might be have a different recipe. So this is the actual photo, zoom with a 200 micrometer width of a PVDF. So you just imagine, yesterday we talked about our hair with about 50 to 70 micrometer. So this is just slightly bigger, 200 micrometer. Then you do the testing with, because this is a hybrid system, which is a piezoelectric and pyroelectric. Piezoelectric, as I mentioned, you can harvest electricity by providing strain to the system, or pyroelectric is about heat. You have a thermal fluctuation, then you can get electricity. So because of the nature of PVDF at beta phase, you can have both piezoelectric and pyroelectric. So if you blow hot air to the systems, you can harvest the heat from the hot air, and also for the blowing of air, I mean the flow of the air, that can provide strain to the materials itself. So that will provide a piezoelectric output. So beta phase of the materials here. Some calculation. So prior to the experiment, you have to calculate basically whether it will work or not at a certain extent, hypothetically, and do some simulation of the micro device. Okay, basically the PVDF film at the beta phase is here as detected by FTSRD. So this will be kind of how you can package the system and the setup in terms of this pad. This is aluminum pads for the electrical conductivity. I mean, for you to harvest electricity from the system. And this is actual kind of thermal camera that try to look into the applied heat to the system and how you can get the electrical power. So the induced power from this small device, maybe the size of 20 times 20 millimeter, then the voltage, open circuit voltage is about 1.2 volt here, okay, the maximum. So that is a quite significant output basically. So, but what we designed is a system that can harvest electricity from hot air. So when you blow hot air to the system of this microsystem, you can harvest some electricity that is good enough for you to power certain sensors or IoT node. Okay, I think time is up. Okay, and another consideration in terms of design is for the multi-probe that later on I will share on this as well on the case study. But I think just to provide some indication of the design consideration here, to design this kind of probe, what we have to consider in terms of the capability of this in terms of making the movement and what kind of materials should be considered from the beginning. Let's say you want to have this as a substrate, what will be the good substrate and what will be good process and electrical conducting material as well. So I think maybe it's better for me to consider it later for the consideration. Thank you.
Thank you, Professor, for the useful lecture of design consideration topic. I have only one question, then I will pass to the other participants. Okay, sir, that re- regarding the residual stress you are talking, that residual stress, na, since it is a micro fabrication, that product is going to the final one. After that, we are not going to do any treatment to remove the heat treatment, remove the residual stress. So, what kind of consideration, design consideration we need to take in order to minimize the residual stress? Uh, can you point out this?
Okay, normally residual stress, as I mentioned before, is also can be mitigated by the process itself. So in a normal process of MEMS design, every step will be evaluated. So when you pass through a certain step, then you do characterization, you do evaluation of the process and the device, whether it's as intended or not what you have produced. So let's say after you deposit certain thin film on your substrate, you will go through a process to evaluate whether this is okay or not, whether it's acceptable or not. So residual stress can be determined at this stage. So if you see that warpage happen or bending happen, then you will repeat the process. Basically, you repeat the process in order to optimize to remove the residual stress from happen. So that is one of the option. Of course, another option is maybe more complicated from the beginning. The design itself must be accommodating to the possibility of residual stress to happen. Yeah. Thank you.
Thank you. Thank you. Thank you.
Sir, I have few doubts, sir. In those MEMS system, you said na, you tell na, sir. While giving heat air, electric will transfer generate. How it will be generated, sir?
Okay, you see some materials, uh, a material called thermoelectric. So the thermoelectric materials is, you can see the thermoelectric material the same as solar cell. Solar cell works with light, with a photon. the energy pack of solar, I mean the photon, uh, you kind of can be converted into electricity by solar cell. So with thermoelectric, it's the same thing, but with heat. Instead of light, but with thermal, with heat. So when you apply heat to certain materials, which normally the category of thermoelectric material, you can get electricity. Meaning to say, when you have heat, the electron will move due to heat pack, which is a phonon. All right, we call it as phonon. So there are two types of material that can do this. One is what we call as thermoelectric. The other is what we call as pyroelectric. So thermoelectric basically work on the basis of energy thermal difference, the delta T, and the pyroelectric works on the basis of thermal fluctuation or temperature fluctuation. So you see the temperature fluctuation, you can harvest electricity, basically, the material can harvest. All right, thank you very much.